Have you ever tried reading a maze from the outside in, layer by layer? Spiral Matrix is a Pattern Mastery 100 classic and a frequent test at Google, Meta, and Amazon. Over 30% of candidates trip up on edge cases or lose track of their boundaries. Master this, and you'll ace any 2D traversal or matrix boundary manipulation question. Let's break down Spiral Matrix using the basic approach, so you'll confidently handle any 2D matrix traversal in an interview. Given an MXN matrix, return all elements of the matrix in spiral order. 2D list matrix, of size MXN. List of integers, values in spiral order. Think of printing all the numbers in a Sudoku board from the outermost cells to the very center, like peeling an onion. An interviewer might ask, how would you read or process data from the edges inward in a 2D grid? What's tricky? Keeping track of the boundaries as you spiral inward. Handling non-square matrices, for example, 3x4, 4x3. Avoiding double counting elements at boundaries. Use 4 boundaries: top, bottom, left, right. At each step, traverse. Left to right, top row. Top to bottom, right column. Right to left, bottom row, if not revisited. Bottom to top, left column, if not revisited. After each traversal, shrink the corresponding boundary. Repeat until boundaries cross. Let's clarify. Check that after moving left/right or up/down, the other boundaries haven't already crossed. Careful handling when there's a single row or column left. Edge cases. Matrix is empty. Return. Matrix is just one row or column. Initialize top equals 0, bottom equals M1, left equals 0, right equals N1. While top less than equals bottom and left less than equals right. Traverse from left to right along top, increment top. Traverse from top to bottom along right, decrement right. If top less than equals bottom, traverse right to left along bottom, decrement bottom. If left less than equals right, traverse bottom to top along left, increment left. Collect all elements in a result list. In the worst case, the time complexity of this algorithm is OMN. We visit each element of the matrix exactly once, where M is the number of rows and N is the number of columns. Now, let's look at the idea behind this solution. We use 4 boundaries, top, bottom, left, and right, to keep track of the edges of the unvisited part of the matrix. We traverse the matrix in a spiral pattern. Right, down, left, and then up. After completing a pass in one direction, we shrink the corresponding boundary. We repeat this process until all elements are visited. Think of it like peeling an onion layer by layer in a spiral pattern. Create a list called Res to store the elements in spiral order. Check if the matrix is empty or null. If it is, return the empty list. Initialize the boundaries, top and bottom for row limits, left and right for column limits. Keep looping while the boundaries are valid, as long as there are unvisited elements. Traverse the top row from left to right and add elements to Res. Move the top boundary down. If top passes bottom, stop the loop. Traverse the rightmost column from top to bottom and add elements to Res. Move the right boundary left. If left passes right, stop the loop. Traverse the bottom row from right to left and add elements to Res. Move the bottom boundary up. If top passes bottom, stop the loop. Traverse the leftmost column from bottom to top and add elements to Res. Move the left boundary right. Return the final list containing all elements in spiral order. So, to summarize, this algorithm first sets up boundaries to track the edges of the unvisited matrix. It then moves in a spiral direction layer by layer, shrinking the boundaries as it goes. This approach is efficient, systematic, and intuitive. Before checking the output, let's understand the problem. We are given a matrix, and the goal is to traverse it in spiral order. Start from the top left corner. Move right, down, left, up, shrinking the boundaries as you go. Continue until all elements are visited. Let's test our function with this matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. We want to traverse it in a spiral starting from the top left corner. Here's why the solution works. Set boundaries. Top equals 0, bottom equals 2, left equals 0, right equals 2. Spiral traversal. Step 1. Traverse top row, left to right. Add 1, 2, 3, then top plus equals 1. Step 2. Traverse right column, top to bottom. Add 6, 9, then right equals 1. Step 3. Traverse bottom row, right to left. Add 8, 7, then bottom equals 1. Step 4. Traverse left column, bottom to top. Add 4, then left plus equals 1. Step 5. Now only the center remains. Add 5. The final result becomes 1, 2, 3, 6, 9, 8, 7, 4, 5. And that is exactly what the program outputs. 1, 2, 3, 6, 9, 8, 7, 4, 5. This confirms that the spiral traversal is working correctly. So, our implementation is correct. It successfully traverses any matrix in spiral order. Accurate, clear, and reliable. Our implementation is correct. It correctly traverses the matrix in spiral order. It handles shrinking boundaries automatically. It works for matrices of any size or shape. In the worst case, the time complexity of this algorithm is OMN. We visit each element of the matrix exactly once, where M is the number of rows and N is the number of columns. The idea behind the solution is to treat the matrix like a grid and move in a spiral using directions. We keep track of visited cells using a separate scene matrix. Whenever we hit a boundary or a cell we've already visited, we rotate the direction clockwise. Think of it like walking along a maze and always turning right whenever you can't move forward. Create a list called Res to store elements in spiral order. Check if the matrix is empty or null. If yes, return the empty list. Get the number of rows M and columns N. Create a Boolean matrix called scene of size M by N to remember which cells have been visited. Define direction arrays. Dr for row movement, DC for column movement. These arrays represent moving right, down, left, and up. Start at the top left corner at 0, 0, with an initial direction index D equals 0, which corresponds to moving right. Loop over all elements in the matrix. We'll visit each cell exactly once. Add the current cell at R, C to our result list. Mark this cell as visited in the scene matrix. Calculate the next row near and column NC based on the current direction. If the next cell is inside the matrix and hasn't been visited, move to it. Otherwise, we've hit a boundary or a visited cell. Change the direction clockwise by updating die to die +1, modulo 4, then move to the new cell in that direction. Finally, return the result list containing all matrix elements in spiral order. To summarize, this algorithm sets up a direction system and a visited matrix, then moves through the matrix in a spiral, rotating directions whenever necessary. Every element is visited once, making the solution systematic, elegant, and reliable. It works for any M by N matrix. The scene matrix ensures we never revisit cells. Direction arrays simplify movement in the right-down-left-up sequence. Time complexity is OMN, and space complexity is also OMN, due to the scene matrix. Now that we've implemented our solution to traverse a matrix in spiral order, let's check how it works on an actual input. We'll see how the algorithm correctly follows the spiral path from the outer layer inward. This input is a 3x4 matrix. We want to collect the matrix elements in a spiral order, starting from the top left corner, moving right, then down, then left, and then up, continuing inward until all elements are traversed. Here's why the solution works. The algorithm maintains 4 pointers, top, bottom, left, and right to track the current edges of the remaining matrix. It traverses the top row from left to right, the right column from top to bottom, the bottom row from right to left, and the left column from bottom to top. After each full traversal of an edge, it moves the pointers inward to the next layer. Step by step for this input: traverse top row 1, 2, 3, 4, traverse right column 8, 12, traverse bottom row 11, 10, 9, traverse left column 5, traverse the remaining inner row 6, 7, and that's exactly what the program outputs. 1, 2, 3, 4, 8, 12, 11, 10, 9, 5, 6, 7. This confirms the algorithm correctly follows the spiral order for the given matrix. So, our implementation is correct. The algorithm successfully traverses any matrix in spiral order, systematic, accurate, and reliable. Breakdown recap. Conceptually, the goal is to return all elements of a matrix in spiral order. The challenge lies in carefully tracking boundaries and ensuring no element is visited twice. Assess recap. A naive approach risks revisiting cells or mishandling non-square matrices. The optimal approach uses 4 boundaries: top, bottom, left, right, and systematically traverses the matrix while shrinking these boundaries after each pass. This ensures every element is visited exactly once in order. Structure recap. The plan is straightforward. Initialize top, bottom, left, and right boundaries. Loop while top less than or equal to bottom and left less than or equal to right. Traverse left to right along the top row. Traverse top to bottom along the right column. Traverse right to left along the bottom row, if not revisited. Traverse bottom to top along the left column, if not revisited. Shrink the boundaries after each traversal. Implement recap. We implemented this with a simple loop, appending elements to a result list as we spiral inward. The code runs cleanly on LeetCode, handling all matrix shapes without error. Check recap. We verified edge cases such as empty matrices, single rows, and single columns. Every element is visited exactly once, giving OM times n, time and OM times n, space for the result. Closing insight. The key takeaway? By managing boundaries carefully and moving systematically, you can traverse any 2D matrix in spiral order efficiently and safely, a versatile skill for many matrix-based interview problems.